Welcome back. I'm Lisa Blackburn. This is my YouTube channel for everything I want to talk about science and math. And today we are doing notes in AP Chemistry on liquids and intermolecular forces. And I need to turn off our little daily board and put it on the notes. Come on, there it goes. All right, so hopefully we can do these fast and you'll get a little bit of time to work on the I do, we do's. Okay. So according to the kinetic molecular theory that was in our last notes, the attractive forces between gas particles for an ideal gas are, starts with an N, negligible. Remember that from your notes yesterday?
Yes. No.
I remember it because I always have to think about how to spell negligible. I don't, that I doesn't seem like it should be an I to me. Negligible. So see, look, no attraction. Our little gas molecules are not attracted. Compare the properties of gas, liquids, and solids by filling in the table. So y'all should know this. Probably learned it in elementary school. Does gas have a definite volume?
No.
No. Does liquid?
Yes.
Yes. Does solid?
Yes.
Yes. Does gas have a definite shape?
No.
Does liquid?
No.
Does solid?
Yes.
See, y'all can do this without me. Does it expand to fill its container?
Yes.
Liquid?
Yes.
Is it no?
No.
It doesn't fill
It doesn't fill the container. And solid? No. Is it compressible?
Yes.
Yes. Liquids sometimes are a little bit, so we're going to say slightly.
Slightly.
Mostly you think of them as no, but we'll say slightly. Okay, and how about solids?
Yes.
No. We're going to say no. And I know that the thing is like ice, what's happening with it being compressed is you can compress it where that little space in the middle of the ice is collapsed, but it's actually becoming a liquid when it does that. So regular solids that don't have solids that can be compressed have air pockets in it, and what you're doing is you're just crushing out the air. Okay, so don't let that confuse you. Do its particles flow readily? Gas, yes. Liquid? Yes. Solids? No. Is diffusion fast or slow? Fast. How about liquids? Slow. If you stir them, they mix pretty fast, but otherwise it's slow. And then solids, we can say very slow, like sometimes over many years, solids might mix some. Is density relatively high or low?
Can you give an example of it, like solids mixing?
I would say with like volcanoes that the magma can be sort of solid as it's cooling, but very slowly it can incorporate other things into
Like the sedimentary rocks?
maybe like sedimentary rocks. They're mixed, yes. It'd be things like that. It'd be like geological processes. Nothing. And I don't know that much about geology. Mr. Myrick, who is here, had like all but a doctorate in geology. If he had taken his classes in the right order, he would have a doctorate in geology. All right, but he's gone now. He might be teaching like eventually at Chattahoochee or Georgia Highlands. If you want to take geology from him, then he might stay retired or he might start teaching again. Is density relatively low or high? Gas, of course, is low. Liquids are high. They're pretty stuck together close. And solids, of course, are relatively high, depending on if it's got air pockets in it or not. Because the particles in a solid or liquid are fairly close together compared with those of a gas, we often refer to solids and liquids as condensed phases. They're more condensed. They're condensed. So see, isn't this all easy so far?
Yeah, that part. Yep.
That's pretty easy. Okay, so in your book, there's a figure 11 to describe how the intermolecular attractive forces appear to change as one moves from chlorine to bromine to iodine. So if you don't really have to look at the figure in your book, just look at the periodic table. What's the difference between chlorine, bromine, and iodine? They're all in the same family and they're getting bigger, right? Okay. So if we want to talk about its attractive forces, that chlorine is going to have the least.
Why?
Because they're not, it's a gas, and they're spread out, and so they're not all that attracted to each other. But then bromine is what? Chlorine is a gas. What's bromine?
A liquid.
A liquid. So it's the molecules are going to be closer, and they're going to be more attracted. And then iodine is a solid. So this one is a solid, and so this is the most. So really it has a lot to do with how close they are and how they're interacting. Yes?
So how close the particles are determine the intermolecular attractive forces?
I can't hear you. Talk louder. You started strong. How close are the particles?
They determine the intermolecular attractive forces, right?
Yes, that has one part of it. But we're going to talk about other things that affect it, like polarity. Okay, so that's what we're going to be talking about. The kinetic energies of particles are usually controlled by changing what? What gives something more kinetic energy in chemistry?
Shaking.
No.
Oh, heat.
Heat, right. It's temperature. Temperature. All right. Describe what happens to the attractive forces between water molecules as water vapor undergoes condensation, turning into drops of liquid water. So first imagine the water is a gas, zipping around, and then what's going to happen to the temperature to get it to condense? Is it going to increase or decrease? Decrease. So as the temperature decreases, the water gas slows down. Does kinetic energy increase or decrease? Decreases. Ooh, see, I told y'all this is easy. And the molecules get farther apart or closer? Closer. And intermolecular forces increase or decrease? Increase, because now they're getting closer together and they can feel each other. Condensation occurs as gas molecules combine to form droplets. Droplets of liquid. So that's condensation. Now explain how increasing the pressure on a sample of gas can affect the attractive forces between particles. So you can get them colder and bring them together, but we can also squish them together. Increasing the pressure brings the particles closer or further apart? Closer. This makes the particles more or less attracted to each other? More. Eventually, the gas will condense into a liquid. Okay, page 1.
Is it possible for a gas to go straight into a solid or not?
Yes. Yes. It's the opposite of sublimation. It's called deposition. Yes?
Is there like a law name for those things that we just wrote or no? Are they just rules? Okay.
Just rules. Kinetic theory of matter. Okay, intermolecular forces. How does the strength of intermolecular forces in general compare to the strength of ionic, metallic, or covalent bonds? So this is really important. You might even want to put a little star by it. This is one of the things they like to test, and it's one of the things that students get confused. Intermolecular forces are much weaker. So what gets confusing is what we're going to be talking about. These are not bonds. These things, ionic, metallic, and covalent are bonds. They're very strong. What we're talking about is just slight little attractions. Okay, just little attractions. But what makes it confusing is one of them is called a bond. It's not, but its name has bond in it. So that's where all the confusion comes in. We should rename it hydrogen slight attraction, not hydrogen bond. But it's not a bond. What is a bond is ionic, covalent, and metallic. And those are much stronger. Everybody got that in your head? Then that's a AP question right there, you know. Okay, referring to the diagramming it right, discuss the difference in strengths between the attractive forces A and B. So here we've got chlorine bonded to hydrogen in 4 molecules. But then we have this slight little force of attraction between the hydrogen that's bonded to this chlorine, but it's going to be a little attracted to that one. Because if you remember, chlorine is more electronegative. It's hogging the electron. That gives this hydrogen a little positive charge. That chlorine is hogging its electron, giving it a slight negative force, and we have a little slight opposites attract there. Can you see that? Okay, so A, that is a covalent bond. So real bonds are much stronger. They have intramolecular forces. A bond is considered intra. That means it's within the molecule a force of attraction. Okay? B is an intermolecular force. That means from one molecule to another one. And A is much stronger than B. Okay? Good so far? Nothing too hard. Okay, so now we're going to talk about enthalpy with this. So here we have the enthalpy of vaporization for hydrochloric acid, and here we have the bond enthalpy for hydrochloric acid. So this one is we're just getting the hydrochloric acid to not be a liquid anymore and to go fly off and be a gas. But it's still hydrochloric. Here we've got hydrochloric acid bonds and we want to break them. Notice that this is a high energy and that's a low energy. This is the energy to convert liquid to gas. That's the energy to break the bond. Explain how the data in the table above supports your answer to part B. Okay, intermolecular forces or intramolecular forces are stronger than intermolecular. So your book says a bunch of times. So bond enthalpy is greater than the enthalpy of vaporization. Okay? It's just saying sort of the same thing over again. Everybody good?
Yeah.
Okay, so here we have a little chart of it. And here you can see that these are chemical bonds. And notice how high these melting points and boiling points are. So these are actual bonds, diamond, beryllium, lithium fluoride. These are just intermolecular forces. These are just our little attractions. And we have several of them listed here. One is called dispersion force. One is dipole-dipole. And one is hydrogen bonding. See, that's where the confusion comes in because that's not really a bond. And notice how much lower these are. Everybody follow that? Okay, it's just saying the same thing another way. What conclusions can be made about the relative strengths of attractive forces from the information? The first 3 bonds are broken. This requires more energy. The last 3 intermolecular forces are weaker, or overcome. They're just overcome, these little intermolecular forces, so it can go fly freeze. And this requires less energy. Okay? Still good? All right, let's move on. So this one's kind of fun. There are 3 types of intermolecular forces that exist between neutral molecules. Name them. Okay, the first one, I don't know why it's called this, but it is called, we need to look it up. It's called London, like England. London dispersion forces. The second one is called dipole-dipole. That's kind of fun. So nice, we named it twice. And the last one is called hydrogen bonding. And I usually just call it H bonding. Okay? Electrostatic interactions can be described by Coulomb's law. We've talked about this quite a few times in this class. Give a brief summary of how electrostatic attractions are affected by the magnitude of the charges and the interparticle distance. So what this is saying is the force is equals to the 2 charges multiplied divided by the distance squared. So there are two factors. The factors have to do with how big the charge is and how close the particles are. We've said that before, right? Okay, so the attractive forces increase, I'll just tell you, I don't think I can make y'all guess it, as the magnitude of the charges, as the magnitude of the forces increase, the charges force, and the attractive forces decrease as the distance between the particles increase. Bigger charges, more attraction. Closer, more attraction. Okay. Based on your answer to this part, the part above, give two specific reasons why intermolecular forces are weaker than ionic bonds. So this is the energy of the intermolecular forces, electric charge, and it's a constant times the charges divided by the distance. So, the charges with the intermolecular forces are much weaker than the ones in bonds. So let me show you why this is. So what it's saying is these Q's are less. They're much weaker, and the distances are what? More or less. They're going to be greater. The distances are greater because they're not in the same molecule, they're adjacent molecules. So they've got less charge and greater distance. And that's why those are weaker. Okay? In 1930, Fritz London, that's why they're called London forces. And you know, it's like I knew that and had forgotten it. Proposed that the motions of electrons, I wonder if it was in London. In 1930, Fritz London proposed the motion of electrons in an atom or molecule can create an instantaneous or momentary dipole moment. So the electrons can just sort of not be evenly distributed. It gets a little negative on one side for a second, and then that can cause on another molecule a positive charge, and you can get this little attraction. There, it's in your book, there's a diagram. Describe what can happen in an atom or molecule when the distributions of the electrons can be arranged asymmetrically, even just for a moment. They can affect the electrons in another atom or molecule. They scoot because they're, there's like, it's all negative, so other negative electrons will scoot out of the way, causing an instantaneous dipole. So the other molecule will respond and it'll get a little dipole. And that causes more dipoles. So it's sort of a chain reaction. One electron, some electrons bunch up, and then they're going to cause all these little scooting away in the other ones. Okay. Define polarizability and explain how this property is related to the relative strengths of dispersion forces. So it is the ease with which the charge distribution is distorted. How easy do they scoot? More polarizable molecules have larger, I'll write it out, larger dispersion forces. So how easy do they get scoot and make these little positive and negative charges? Can I scroll? It just says distorted, larger. See, I tried to make y'all not have to write a lot because there's not a lot to this. Okay, so here are boiling point data. We have neon, argon, krypton, xenon. They're all noble gases. What is happening to the boiling point as they get bigger?
Increasing.
It increases, right? Okay, so that's what we're seeing from our data. And what we can say about it is the dispersion forces increases with the size of the molecule. Bigger clouds are more polarizable, and molecules with bigger electron clouds have stronger dispersion forces. So that's our next sort of big point, is as these molecules get bigger, they're going to have more of these forces, as they have big clouds that can do more scooting. Okay, note the polarizability of a molecule and the dispersion forces generally increase with the size of the atom of the molecule. When you compare two substances on the basis of their London dispersion forces, you should always talk about the size of the electron cloud and how polarizable it is. Do not explain a boiling point trends as follows. So like this is a AP question and this is the wrong answer. X has a higher boiling point than Y because it has a greater mass. That explanation would be incorrect. Your grader would count it wrong. It's not about mass, it's about how big the cloud is and how squishy it is. Okay, moving along. Okay, dispersion forces increase with contact between the molecules. The shape of the molecule affects the surface area and how much it comes into contact with the neighboring molecules. Which of the following molecules has the lowest boiling point, the highest boiling point? So if it has a low boiling point, it is not very attracted to the other molecules. It doesn't have many forces. If it has a high boiling point, it is attracted. Everybody can imagine that? Okay, so these are all C5H12, pentane. These are called isomers. They are taking the pentane and rearranging it to new ways. Like this one, they chopped off the end and stuck it here. And here they chopped off two ends and stuck one on top and one on bottom. When you do this, they have different names. And I used to get to teach it before they changed the standards. But you'll learn it in organic chemistry. It's pretty easy. But that's not what we're talking about. What we're talking about is which of these. So this one has the largest surface area. This one has a smaller surface area. So do you think this would have more or less attraction, dispersion forces with more surface area?
Less attraction because it's bigger, right?
Wait, which one would you say?
Less.
You think it's going to be less attracted to another one?
Well, because like there's more to spread in, and so they're farther apart, I thought.
This isn't attraction to itself. This is attraction to another molecule in the beaker. So there's a bunch of these. Are they more attracted to each other or this one? Then we got a beaker of this and a beaker of that. Which one is going to be more stuck together? And this one has a greater surface area. That's your hint.
Greater attraction.
Greater attraction. That's right. More attraction. Because there's more area for it to get attracted to. It's like if you're gluing something. And it's only glued in one little place as opposed to putting glue over the whole thing. It's going to stick more, right? So smaller surface area has less, or it has weaker, we'll say weaker dispersion forces, okay? So, and we can see that because this one has the highest boiling point, and this one has the lowest boiling point of these. Okay. So dipole-dipole forces occur in polar molecules. So if a molecule is polar, do you have a question?
Yeah.
Yes.
So for the medium boiling,
Talk loud. You have a soft voice.
so for the medium boiling point, like what's the dispersion force for that?
It's got dispersion force, but it's got an in-between. It's got an in-between surface area. So it's in between how much room it's got to glue, how much these molecules can be attracted to each other. So its boiling point is going to be in the middle, and its dispersion is going to be in the middle. And now we're going to talk a little bit more where these dispersion forces come from. Okay, so all the molecules have London dispersion forces. What we're talking about right now is just from the scooting. Kyler, do you have a question? No. No. Okay. Yeah, y'all just look like you're maybe had a question.
Oh no, it just it smells weirdly here.
It smells bad.
It smells like rotten eggs.
The gas was on earlier, but Atticus Corn came and made sure they were all off. So maybe we need to check it again. I turned on the vent, but I don't want it on during the video. So let me talk real fast and then we'll turn on the vent. Okay, dipole-dipole forces occur in polar molecules. Draw the structural formula of two CH-Cl3 molecules. Label the positive and negative ends of each molecule. Use a dash line to show the dipole-dipole forces between them. So remember that chlorine is more electronegative than carbon. Okay, so what we want to do is we want to just show where these forces of attraction come in polar molecules. So I've got a carbon in the middle, and it is going to have a chlorine, a chlorine, a chlorine, and a hydrogen. Okay, everybody follow that? Now with this, for this bond, carbon keeps the electron the most. But with these, chlorine keeps the electron the most. So our arrows go out toward the chlorines and in toward the carbon there. Okay, so here I've got another one. Hydrogen bonded to a carbon, bonded to a chlorine, and another chlorine, and another chlorine. Okay, and so here, this over here is a little bit positive. This is a little negative, that's a little negative, that's a little negative. Right here, what is this hydrogen a little bit?
Negative.
Positive. Remember, hydrogen's a wimp. He never gets his electron. A little bit negative, a little bit negative, a little bit negative. So do you see where there's going to be attraction right there? So we're going to change the color and make it a little easier to see. But right here, I'm drawing a dotted line. There's a little force of attraction, and this is called dipole-dipole forces because this molecule has a dipole. Remember, it's positive on this side and it's going that way with the negative. This one has the same thing. It's more positive on this side and negative that way. So they're attracted to each other. This negative is attracted to that positive because these molecules have dipoles. Okay, not too hard?
I have a question.
Mm-hmm.
What were you saying about the carbon and chlorine attraction thing?
Okay, so how do you know the polarity of a molecule? Is you have to understand the electronegativity. And hydrogen is not very electronegative. It always loses its electron. Carbon is more electronegative than hydrogen. So for this bond, hydrogen is more positive, carbon is more negative. But chlorine is much more electronegative than carbon. So between here, they get the electron more than carbon does. These guys get the electron more than carbon does. Carbon gets more than hydrogen. And that makes polarity go this way. And this is because polar molecules are asymmetrical. So therefore, they get this dipole-dipole moment, and that's one of their forces. Everybody's got London forces, but polar molecules also have dipole-dipole. That was our force number 2. So if you understand, there are absolutely questions on this on the AP test. So make sure you understand this. It's not hard, but it's going to be on there, I promise you. Okay, moving right along, page 5. We're rocketing along. Okay, so we have 2 molecules here. Which one of these is polar?
The left one.
That one, right? Remember this nitrogen has an unshared pair over here, a big old negative blob on this end, right? These hydrogens are all losing their electron. They're all positive. You can see that? This is the same all over. It's symmetrical. It's a little positive everywhere you look. A little positive on the outside, okay? So of these 2, which one is going to have a higher boiling point? Which one has no attachment and it's ready to run off and be a gas? And which one has attachment and it's going to stay in the liquid? Which one has the higher boiling point? Which one wants to stay in the liquid?
BP.
That one, because it's all stuck together. It's polar, so this has a higher... It has a higher boiling point. This one, nothing's holding it back. It has no attachments. It's not attracted to anything, so it has a lower boiling point. Okay, so AP loves this question. Who's going to have the higher boiling point and why? There you go. Identify which of the substances shown above has a higher boiling point. Justify your answer based on structural features of each molecule and the type of intermoleculars the experiences. So this one is our polar one. This one is our nonpolar. Polar is asymmetrical. Its dipoles don't cancel out. Now, you can have polar bonds, but it'll be a nonpolar molecule if all the bonds cancel out. It has the London dispersion forces and dipoles. That's fun to say. So it's stronger. This one is nonpolar. It's symmetrical. Its dipoles cancel out. It's got dipoles, but it's equal in the opposite of all directions. It only has London dispersion forces. So the one that's going to boil easy is the propane. That's propane. Okay.
That's not a blank, right?
What?
Forces. Dispersion forces, blank.
I like London dispersion forces is a lot to write. So it is abbreviated LDF. And if you see LDF written, they expect you to know that is London dispersion forces. It's an abbreviation you're expected to know. Yes, ma'am.
So is there like a correlation between like non-polar, polar, and boiling point? Like
Yes, absolutely. So if something is nonpolar, it evaporates easily, it boils easy. If it's polar, it doesn't. It stays in a liquid. So water is polar. Takes forever for it to boil, right? Alcohol, rubbing alcohol, is nonpolar. You put it on your skin and it's cold. It's already evaporating. It's so ready to be a gas, it just does it so quick, you feel that cold on your skin. Okay? All right, so here we have some things. We have water, hydrogen fluoride, ammonia, and methane. And we see that their boiling points, see, water is way higher. It's polar up there. And we can also see that sort of just the trend with these things with the molecular weight. So it says, explain the boiling point trend for the group 4A hydrides. So all are nonpolar. Are nonpolar, tetrahedral, symmetrical, and have London dispersion forces. So what we're talking about is the hydrides, those, okay? So if you look at this one right here, that each one of these, they're in the same family. You've got carbon, silicon, germanium, tin. Do you see how that's all in the family? All of these are in the same family, sort of moving along. And you can see that there's this trend where boiling point goes down, then it comes back up. So how come? Because they might all be the same, but the trend is because larger molecules are more polarizable and have stronger London dispersion forces. So we can see, we learned that earlier, that the bigger the molecule, the more it is affected by these forces. The more squishable its electron clouds are. And we can see here that that affects boiling point too. That that these forces come into play more if it's a larger molecule. And it affects boiling point too. Okay? Which of the three hydride molecules in the graph have unusually high boiling points compared to the others in the series? And it was water. The water was really high. The hydrogen fluoride was really high. And the ammonia is really high. So why? And this is our new kind of bonding we're going to learn about, our new force, and it's called hydrogen bonding, okay? And it is an attraction between hydrogen in a polar bond, especially hydrogen with fluorine, hydrogen with oxygen, hydrogen with nitrogen, and a non-binding, how do I write this, pair I will put electron pair, on another nearby small electronegative ion, usually F, O, or N. So this is like the strongest of these intermolecular forces, and it's when you've got a hydrogen and it is getting attracted to an unshared pair. Because remember, hydrogens are just so positive, they're so wimpy, and their electron is stolen, they're positive, and they see that beautiful electron cloud over there, and they go cuddle up to it. And then you get hydrogen bonding. Okay, next, draw two ammonia molecules. Using a dashed line, draw a hydrogen bond between them. Make sure you know the difference between a hydrogen bond and a covalent bond. Is it a real bond, hydrogen bond? No, it's just a force of attraction. Okay, so let's draw the nitrogen. And how I'm going to do it is I'm going to put a hydrogen up top, a hydrogen on the side, and a hydrogen on the side, and there's this unshared pair. Okay, now I'm going to draw another one. I'll do it like this. A hydrogen to the nitrogen, to the hydrogen, to the hydrogen, and here's another unshared pair. So there's going to be a force of attraction. I'm going to change my color. We'll make it blue. And it's going to be right here. Forces of attraction that aren't real bonds are drawn with a dotted line. So you can see that. And do you see how another hydrogen will come find that? And it's all going to stick together. Okay? Circle the molecules below that are able to participate in hydrogen bonding. The hydrogen must be bonded to an F, O, or N. Okay, so can this one do hydrogen bonding? No, all those hydrogens are to a C. Can that one do hydrogen bonding? No, all those hydrogens are to a C. Can that one do hydrogen bonding? Yes, because the hydrogen is bonded to an oxygen. Okay, how about that one?
Yes.
The hydrogens are all bonded to chlorines. It's got to be to F, O, or N. So that one is no. How about this one? Yes. The hydrogens are bonded to.
Wait, I have a question.
Yes.
For that one, that's.
Talk loud.
Okay,
You always say you start strong and then you get quiet.
my fault. Okay, the one in between the two circle ones, right? Can it have like some type of? Never mind. Not stuff.
It's gonna have some attraction, but it's just not hydrogen bonding because it's got unshared pairs, and and so there's gonna if you had a whole beaker of this stuff, the hydrogens on one molecule might be a little attracted to those unshared pairs on that oxygen, but this is gonna have a whole lot less force of attraction than these, where hydrogen is bonded to F, O, or N, because these are so electronegative, they're going to be pulling that electron away from hydrogen, and then it's got those unshared pairs for other hydrogens to be attracted to. So, all right. So how does hydrogen bonding explain why water expands when it freezes? So look, here's my water, and let's go ahead and draw in some little attraction lines so we can see that the hydrogen's attracted to that oxygen. The hydrogen is attracted to that oxygen. That hydrogen is attracted to that oxygen. That hydrogen is attracted to that oxygen. That hydrogen is attracted to that oxygen. And that hydrogen is attracted to that oxygen. Do you notice how many water molecules I have here? 6. So do you know why every snowflake has 6 points? Because of this. It's reflecting this geometry. It goes back to that video we watched a long time ago about how there's something in the macroscopic world that reflects the microscopic. Okay, so when they bond like this, do you see how there's a big old hole in the middle? That big old hole in the middle is air. And that's why ice floats, is because when water is a liquid, there's no hole in the middle. It just all sticks together close. But when it gets into a solid, it makes this 6-sided hole in the middle. So the H bond makes it spread out. And causes a cavity. With liquid, it is closer. Okay, so here's another application. An ion dipole force exists between an ion and a polar molecule like water. So label each one. So this is salt, These are the hydrogens in water. What ion would they be attracted to when salt breaks up, the sodium or the chloride? These positive hydrogens are going to be attracted to the sodium or the chloride? The chloride. So we got the chloride right here, and it could be any negative ion could do that. And so what goes in this one? The sodium. All right, and so notice that the negative water into the water lines up with the positive sodium. Okay? All atoms and molecules experience London dispersion forces. All of them. Only polar molecules experience dipole-dipole. So nice, they named it twice. Only a molecule that has hydrogen directly bonded to nitrogen, oxygen, and fluorine experience hydrogen bonding. So if you remember this, you're going to get some questions right on the AP test. If an ionic substance is dissolved in a polar substance, then ion dipole forces will be present, and that's what that was. Okay? Feeling good about all this? It's all pretty easy, isn't it? Okay. Now here's a little kind of question that you might get on the AP test. Match the following 6 substances with their boiling point. Justify your answer. The boiling points are these, and here are our substances. 1-propanol, 1-fluoropropane, methane propane, 1,3-propanediol, nailed it, and calcium oxide, okay? So if we look at this, which one let's see about how we're going to do this, how I want to go through. Now let's find, okay, which one of these do you think has the lowest boiling point? Which one would have no intermolecular forces hardly at all? It's nonpolar, it doesn't have hydrogen bonding. Can you pick which of these is symmetrical?
Calcium oxide.
Which one?
Calcium oxide.
That's ionic. So is it easy to boil the salt? No. So it's going to be super high. In fact, it's going to be the highest. Okay, so this one is 2850. That one is the highest. Okay. So we did that one. Okay, now on the other hand, which of these is little, symmetrical? Methane, right. So it is nonpolar, so we know it's low. And the other one that is nonpolar is this one, propane. Do you see how symmetrical that is? Very nonpolar there. And of the 2 of these, which one do you think is lower, the little one or the bigger one? Which one is easier to fly? Is it easier to bounce a little kid up there or a big kid on the trampoline? A little kid. So this is the lowest. This is the one that's negative 161 degrees Celsius. And this one is the next one. It's negative 42 degrees Celsius. So, you know, propane's a gas, methane's a gas, that all makes sense, okay? So now we gotta look at these in the middle, okay? So what we have here is 1-propanol. It's got a hydrogen on an oxygen. We have 1,3-propanediol, and it's got 2 places for hydrogen bonding. And then we have fluoropropane, where fluorine is attached to a carbon. So which one do you think is the next one that doesn't have much force of attraction? Do you think it's this one with 1 hydrogen bond, 2 hydrogen bond things, or no hydrogen bond things? Which one is going to be more likely to not have forces on it? The one with no hydrogen bond forces. Do you see that one? So this is our one that is negative 3 degrees because it's got fluorine, but it is bound to that carbon. It's not bound to a hydrogen. Can you see that in its structure? So that one's our negative 3. Okay, and now we have these 2, one with 2 hydrogen bonds or 1 hydrogen bonds. So the one that's going to be lower is which one? 1 hydrogen bond or 2 hydrogen bonds? 1 hydrogen bond. So this one is the 98 degrees, and this one is the 211. Okay. That was good. Do y'all understand? Now, so why was it? The first thing is the ionic bonds are the strongest, so that's why that one is so high. And then the most volatile is nonpolar. How do I write this? Like that one is the most volatile, methane. So, but I want to say that because it's nonpolar. I'll just put methane. CH4 is the most volatile, and we'll put nonpolar small. So that's how we knew that that one was going to be flying off the most. Blank is more volatile and it's bigger. That's our propane. C3H8. Can I write it like that? Do y'all follow that that's the same thing? 3 P's. So dipole is stronger than London dispersion forces, and dipole is weaker than hydrogen bonds. So that's how we were able to figure all those out. Give y'all a minute to write that. Okay, can I scroll? You got that one? Okay. Select properties of liquids, okay? Viscosity is the resistance of a liquid to flow. How thick it is. There used to be a lot of oil commercials on TV where they would talk about that they would not have viscosity breakdown. You didn't want your motor oil to get thin and your parts rubbed together and wear. Explain why decane, C10H22, has a greater velocity than C6H14. Both are nonpolar, but decane is larger and it is more polarizable and therefore has a greater viscosity. So this is what I always think about this. Back when I used to teach this more in chemistry before they changed the standards, we did a unit on oil, on petrochemicals, to build or to burn. It was a curriculum from American Chemical Society. And it had the fractional distillation of petroleum. And they showed you what temperature each petroleum derivative was boiled off: propane, methane, gasoline, kerosene. But the biggest one that is so big that it's a solid is asphalt. Asphalt is a derivative. And if you're thinking about how thick these things are, the bigger the molecule, the less it flows to the point where asphalt is a solid. Now, can asphalt flow? If it gets hot enough, it'll melt it and it can flow. But it doesn't flow very readily, does it? When you drive across the road, you're not thinking, oh no, this road's about to flow off the road, into the ditch. It doesn't. Okay. Explain why glycerol has a greater viscosity than propanol. So what is the big thing you see different in glycerol and propanol? You see it? This one's got 3 hydrogen bonds, and that one's got 1 hydrogen bonds. So it has, we'll say, more hydrogen bonds, and that gives it a greater viscosity because it's all clinging together. It's not flowing. So propanol is like rubbing alcohol. Glycerol it's tackier, it's thicker. Explain how the viscosity of a liquid is affected by increasing the temperature. I already told you. So, and y'all probably know it too. Okay, so you decide you want some hot syrup on your pancakes. Is that syrup going to be thicker or thinner than cold syrup? If you heat it up, it's going to be thinner, If it's cold, it's going to be thicker. So high temperature means you have an increase in kinetic energy to overcome these forces. So temperature, if a temperature increases, viscosity decreases. It's less thick. So there's our pancakes with some. That sort of looks kind of cold, doesn't it? It's not running down too fast. Okay, next idea, which is kind of fun, is surface tension. You ever seen a bug walk on the surface of the water? Wondered how they did that? Go to White Oak Park, go to the duck pond, and you will see bugs walking on that pond. Okay? So using the diagram right to explain why certain liquids experience surface tension. So the reason why a bug can walk on the water is because of surface tension. How that works is, here, these water molecules are all pulling on each other in every direction. But on the surface, they can only pull down. There's no water molecule on this side to pull up. You follow that? So all the force is going down, down, down so strong, it squishes the molecules together closer, and it makes this like energy skin. And it's like a little skin on the water where there's a force that's holding these molecules together where it's great enough where a bug can walk on it. So that's kind of interesting. So on the surface, all forces are on the surface, all forces are down. Oops, why is this not writing? Let me scroll up. Okay, on the surface, all forces are down. Oh, please write, come on. Sometimes I have to close this out when it starts doing this. Sometimes you can change colors and they'll start being good. No. All right, I'm going to close it and open it again. Sorry, technical difficulties. But at least I know what to do. I'm going to say, close it, and I'll say, you sure we'll leave? We're going to leave. That's right.
I've yet to be able to stay awake through the whole entire packet.
All right, let's see, we're going to put on draw. We're going to put on red.
About to go to sleep.
We're going to try a little decrease. All right. On the surface, all forces are down. So the molecules are pulled in. The surface area becomes less, it decreases. The result is like an elastic skin. You can see how those molecules are closer. Okay, what are attractive forces experienced by these liquids, both of which have high surface tension? Okay, so we got water and mercury. Okay, so what big force of attraction does water have? It's got London dispersion. Does it have dipole?
Hydrogen.
And hydrogen bonding, right? So the big one here is it's got hydrogen bonding. The strongest one is hydrogen bonding. And what about mercury? What kind of bonding does it have?
Ionic.
It has metallic bonding. Remember, that's one of our kinds of bonding where they all share their electrons. They get to run free and wild. So that is why both of these have high surface tensions, both mercury and water. See the figure at the right. The meniscus of water looks like this. It goes down because of the adhesive forces between the water and the glass are more or less than the cohesive forces between water molecules, and it is more. So it's sticking to the glass. In the meniscus of the mercury, it goes up because the adhesive forces between mercury and glass are less than the cohesive forces between the mercury atoms. So the water also sticks to the glass. Not only does it stick to each other, it sticks to the glass. Mercury doesn't. Explain how capillary action works. Did y'all learn capillary action in biology? Do you remember that?
There's capillaries, which are like the smallest blood vessels.
That's true. That's true. But it has to do with trees. And they don't have blood vessels, okay? So this is what capillary action is if you have a tube that is small enough, water can pull itself through, but just based on these forces without a pump. So think about the redwood forest. the giant sequoia trees. They can drink water out of the ground and it goes all the way up to the leaves with no heart to pump this water up for them. And it's all because of capillary action. It's because of that force of attraction between the water and a small tube to the side of the tube. So that's what capillary action is. So in a small diameter tube, adhesion forces between the liquid and the wall increase the surface area, and the surface tension reduces, and the cohesion pulls the liquid up until gravity balances these forces. So you're not a redwood tree, you've never seen it in yourself, but you might have been to the doctor and they prick your finger and they squeeze it and get a little bit of blood, and then they take something and hold it to the blood and it sucks it up into the thing to go test your blood. That does that by capillary action. There's not a little pump in that thing. They touch the blood and it just sucks up because of capillary action. So next time you get your finger pricked, look and watch that, okay? All right, so phase change. So this was your question earlier about phase change, Titus. So we can have something go from a liquid to a gas, and it's called evaporation. So you see how this chart works? Okay, if it goes from a solid to a liquid, what's that called? Melting. Good. Okay. If you have something go from a gas to a liquid, what is that called?
Precipitation.
Condensation is what we're going to call it. In science class, to make a precipitate is usually to form a solid in a liquid. Condensation. Okay. Now we could have something go from a liquid to a solid. What's that called? Freezing. Okay, now if it goes from a solid to a gas, what's that called? Sublimation. And then this is the new one that he didn't know earlier. If it goes from a gas to a solid, it's deposition. It's to deposit. All right. Good. Moving on to number 9. Okay. Endothermic and exothermic. Melting, evaporation, and sublimation. Do you think those are endo or exo? Does sweating and evaporate cool you off or heat you up? It cools you off. Hello. Good. How are you? You may. You're welcome. Giovanni, you need to go see Miss Hayes.
Okay.
Okay. So, endothermic. It takes energy to melt something, right? It takes energy to get to evaporate. You have to put energy in to get to sublime. It gives off energy, it's exothermic, to freeze. It gives off the extra energy and it becomes a solid. Gives off the extra energy and it condenses. Gives off the extra energy and it deposits. Okay? Define enthalpy of fusion and enthalpy of evaporation. Enthalpy of fusion is the amount of heat required to convert 1 mole of solid to liquid at a normal melting point. And energy of evaporation is the same as above, but you're going from liquid to gas. Yes?
Okay, question. Is shooting a gun endothermic or exothermic?
We got endothermic and exothermic. All right, put the thermic for you.
No.
He said it's shooting a gun, endo or exothermic.
What?
He said it's shooting a gun, endothermic or
It's shooting a gun, endothermic or exothermic. It gives off heat. It's exothermic. It's combustion. Okay. All right, let's move on. Explain why heat of vaporization tends to be larger than heat of fusion. Okay. Heat of fusion, if you're going from solid to liquid, some intermolecular forces are broken, but not all of them. So if you go from solid to liquid, you're breaking some intermolecular, but a lot of them are still there. But heat of vaporization from liquid to gas, all of the forces are broken. They have to overcome them all so they can fly off and be a gas. And that takes more energy. Okay, phase change. There's our phase change diagram we're familiar with. Okay, and it says, identify the segments of this heating curve that would involve the equation Q equals MC delta T. And it's only where there is a change in temperature. So see, there's no change in temperature in BC or DE. So the places that have Q equals MC delta T would be line segment AB and CD and EF. That makes sense? Okay, so we only use it there. Okay, so here's a little bit complicated heat change in this thing. Miss Korn's honors did it and mine didn't. I simplified this problem in my honors class, but we're going to go through it now. So in AB, we're going to use MC delta T. So if we read our stuff here, our mass is 9 grams of ice. So for all of these, it's MCAT, where there's a delta T. So AB is one of them. So that's going to be 9 times the C, which is for ice 2.03. And that's the thing that y'all didn't learn in my class, times the change in temperature, and it changed 10 degrees. So that equals 182.7 joules. Okay, so then the next one, BC, what we do here is we're going to multiply our moles, and they tell us that we have 0.5 moles, times our kilojoules per mole, which is 6.01. So that's our conversion there, and it's 3.005, and that is in kilojoules. So if we're going to add them all up, we got to convert this from joules to kilojoules. We got to move our decimal point over 3 places, so it's 0.182 kilojoules. Okay, the next part has got a delta T, so it's 9.
Miss Blackburn, can we go back to BC? Why are there only 2 numbers?
Because there is no delta T. The delta, if you look at BC, it's flat.
Okay.
No delta T. Okay, so we approach the problem different. Here we're doing it again, so this time we're doing 9 times the C for water, 4.18, times 100, because that's what our delta T was this time. So this equals 3,762 joules, but we should convert it to kilojoules because I think we add them all up at the end. 3.762 kilojoules. Okay, DE is another place where there's no delta T, so we just go with the moles, 0.5 moles, times the kilojoules per mole, and it's 40.67. And so for that one, we get in kilojoules 20.335 kilojoules. And then the last one, we got the delta T again. It's 9, and our C for this one is 1.84. And our temperature change is 10. So for that one, we got 165.6 joules, but we need it in kilojoules, so move the decimal point 3 times. 656 kilojoules, yep, and then they want us to add them all up. Hold on 1 second. 27.5 kilojoules, put a box around it. Okay. You want to scroll up? Yep.
No, I have a question.
I have a question.
okay?
So on EF,
What?
on EF,
EF,
yeah, why is it changing temperature to 10?
because if our little graph here, it only goes up 10 degrees. See right there?
That looks like 25 degrees.
It does look like 25, doesn't it?
Yeah.
Let's see what it says here.
I feel like those
Calculate the heat, need to convert it to -10 into steam. Water at 110. They would just stop at 110. There you go.
Okay. That
I
makes
also
sense.
have a question, Brent.
Yes,
Where are the 0.5s coming from?
that's the moles. They told us, they had us convert it. That's the amount of the moles of water. So we need to convert grams to, so the molar mass of water is 18.
Okay.
So it's half a mole, because we only have 9 grams.
Why did we not have to, why did we change it? Like, if we're doing MCAT and they're all the same form, then why do we only do it for 2 of them?
For
I know
the
it's
two,
exactly
we're,
the same,
so this is latent heat, that's sensible heat.
Okay.
Here, you add heat, but it doesn't change the temperature, and the way you get the kilojoules is different. Instead of doing the MCAT thing, you just multiply the moles times the kilojoules per mole. And then the moles will cancel out, and you'll be left with kilojoules. Yes,
Okay, so I know you said that the 10 came
from here,
Wait, that's where it came from?
that's where it came from.
A, B.
Okay, our water is going to 110. So the last delta T is from 100, where water boils, to our stopping point, 110.
But what about AB?
AB, because we started at -10, and then we went to freezing, which is 0.
Okay.
And 10 minus 0 is 10.
Can you write down the formula we use for the moles kilojoules thing? For B, C, and D when it's latent heat?
So it is the heat, it is the moles times the kilojoules per mole. So, I guess I'll just write it here. So, we'll write BC and DE equals number of moles times the kilojoules per mole. Is that good?
Thank you.
You're welcome. All right, can I scroll?
No.
Yep. All right. Almost at the end here. This little bit, last bit is a little easier. Cooling. A liquid below its freezing point without becoming a solid is called supercooling. So how do you do that? It's that the molecules are for some reason are not getting organized into their crystal lattice, okay? So sometimes the heat is removed so rapidly the molecules can't organize, and sometimes energy or dust can come out, can make it re-solidify. So some of y'all have done this. You got a water bottle out of a really, really cold refrigerator, and it's liquid. But if you hit it really hard on the bottom, it goes and all becomes a solid. Anybody ever done that? So if you haven't, there's videos on it on YouTube. But what it is that little bit of energy can make it do that. But for some reason, even though it's below freezing, the molecules didn't organize. And sometimes I think it's like when it's a refrigerator is nearby, lots of people walking, the floor keeps vibrating and giving it a little jostle so the molecules can't line up. Because the one place I used to know where it used to always do it was this little fridge where the floors weren't real stable and little kids were running by it all the time and just stomping their feet. Okay, explain why a substance cannot become liquefied at a temperature above the critical temperature. So what is critical temperature? It is a temperature where the kinetic energy of the molecules is so high they are more than the intermolecular forces. So it can't become liquefied because those intermolecular forces are being overcome, and it causes a liquid state, or it causes a suspended state. What did I want here?
Maybe we just call it
Yep, it causes a liquid state. Yep, a liquid state. No matter how much a substance is compressed, a liquid can't form. So this is where it's so hot, it can't change states. It's got too much energy. Okay, last bit. How's our time? Oh, we're out of time, aren't we? Yes. So sad. We'll have to do our last little bit with the ghost later. Like, share, subscribe. Science is great.